about W and 4 photon signature, and W for B, and W to B and 2 tau. And then I will conclude. Next slide. Okay, so the standard model, so is just as you know, so it's the standard model is a quantum field theory based on non-abelian gauge symmetry, and the gauge group is SU2 left cross U1 hypercharge. So you have a set of fermion, quarks, and leptons, which interact by exchange of some gauge particles, the W, Z, and the photon and gluon for the strong interaction. Okay, so when you, next slide, when you write down the, well, as we know, so that the this gauge boson are they have mass, and so the problem of the standard model is to explain the origin of mass of those particles. And we know that this gauge symmetry is spontaneously broken down to U1 electromagnetic, which is the residual symmetry that remains. And so one of the mechanisms that we know is broad-angular mechanism, which we call also the Higgs mechanism. Okay. So the particle of the standard model are, this is the, for the lepton, so we arrange them in the lepton, in doublet like this, and for the quark you have up and down, also they are in doublet, SU2 left. And the right-handed component of these particle are singlet under SU2 left. So the gauge bosons, so we have two sets of gauge bosons, W, which are isotriplet of SU2 left, and you have also B mu, which is a singlet under U1. So when you write down the Lagrangian of at least the kinetic term of the fermions, so, and if you ask for local gauge invariance, you should replace the normal derivative by the covariant derivative, which is given here in the top. And so this, when you try to ensure that your Lagrangians respect the gauge symmetry at the local level, so you not only describe the kinetic term for the fermion, but also you predict the interaction between the gauge boson and the fermion and all the fermions there. Okay, and same things happen when you try to write down the kinetic term for the Higgs fields. You not only give you are not only giving mass to the gauge boson, but also you introduce some, you get some interaction between the Higgs bosons and the gauge boson, between the Higgs and the gauge boson as well. Next slide, please. Okay, so this is the Higgs mechanism. So we introduce scalar doublet with two components, phi plus and phi minus, and this is the scalar potential of the scalar field. And so you see it. So this is the scalar potential, and see this is it comes with the mass term with negative sign here, and this is just introduced by hand. So we don't actually, in standard model, we don't understand quite well why this minus sign. If you try to extend so this scalar potential to, I mean, if you do the supersymmetric version of the standard model, and so you write down the scalar potential of the minimal supersymmetric standard model, for example, and if you do some renormalization group equation running, you can start with the scalar potential at some high scale where all the mass are positive, but when you do the running down to the electroweak scale, you realize that for the standard model X, so this mu term becomes negative. And this is mainly due to the presence of the top Yukawa coupling, which is quite strong. Anyway, but this is another story. Okay, so the scalar field develop a vacuum expectation value. So the neutral component which acquire this vacuum expectation value in order not to break the charge. So we ask that the neutral component which develop the vacuum expectation value. So the minimum of this potential, the minimum energy value is not at V equals 0, but on this circle that you can see here. And so all those points on the circle, they satisfy this relation here. But we say that we have breaking of the symmetry when the Higgs field will select one particular direction of this circle. Next slide. So if you do some inspection of the spectrum of the standard model, so before the electroweak symmetry breaking takes place, you have this isotriplet W, it has 3 components, so it's 6 degrees of freedom. And you have one singlet BMU, which is 2 degrees of freedom, okay? And the Higgs field has two complex components, which is 4 degrees of freedom. So in total, you have 12 degrees of freedom. After electroweak symmetry breaking, so you generate the mass for the W's, the mass of the Z. So this becomes a gauge boson which has mass, so it's 3 degrees of freedom each, so which is 6. And the Z is 3 degrees of freedom, but the photons, as we know, remains massless, so it has only 2 degrees of freedom. So if you do the counting, so you have 6 plus 3, which is 9, plus 2 is 11. So there is 1 degree of freedom missing, so which is the Higgs particle. So it should show up somewhere. So if you want to have this, the balance between before and after the symmetry breaking, so there is one particle which should show up. And this is what we discovered in 2012 after many, many years of investigation at lab, Tevatron, and also at the LHC. So it was discovered in 2012 by Atlas and CMS. Okay, next slide. So now we have experimental proof, but I will try to convince you that just using unitarity principle that this particle exists. So if you compute this WW scattering and you try to see if this the amplitude is unitary at high energy. So if you compute only the first term, which is the quartic diagram. So the quartic diagram, if you write down the Feynman rules and then you square, so you get that the amplitude of the quartic term is proportional to S squared. So S is the square root of S is the center of mass energy of the scattering W, okay? So this is proportional to S squared, which is very dangerous because if S increases, so this will become very, very large. So if you include the first diagram with T channel with the exchange of the photon and the Z, so then you get a term which is similar to the quartic one with negative sign, and you get a second term which is proportional to S and G. G is the gauge coupling constant, okay? So if you sum just the first two diagrams, so you see that the quadratic dependence of S disappear. And so if you add just the first two diagrams, so you have this, it's G squared times S, okay? Only this term remains. So then if you add the third term with the Higgs mass, so if you assume that the coupling between W and the Higgs is just GHWW, so if you want to cancel, because this dependence of S is quite large, when S becomes quite large, so this is divergent, okay? It's increasing, okay? So if you want to cancel this, so this GHWW should be related to the gauge coupling also, and also to W mass, okay? So this. So this coupling is. We know that this coupling here is just GMW. If you compute this from the covariant derivative of the Higgs, you find that this coupling, I mean the Higgs coupled to two W's is just G squared V. which is GMW. So if you put it back here, you see that this term with the Higgs exchange exactly cancel this dependence of S here. And so you have only the remaining term which don't have any dangerous behavior as function of S. Okay, and so this proved that in the non-abelian gauge theory, so this exchange of this Higgs particle is necessary to restore the unitarity of the scattering amplitude of the Ws. Next slide, please. Okay. So as I said before, so we already in 2012, we LHC at the LHC Atlas and CMS discovered the Higgs boson, and so what we used to call the golden mode with the discovery of the Higgs boson in the channel Higgs decay to 2 gamma, okay, and also Higgs going to 2 Z's. And so, and now after more than a decade of running, of taking data, so we know that the Higgs mass is given by this value, which is quite spectacular. If you see, the error is to the order 0.1 GeV. Nobody in the beginning was expecting such high precision, but I mean, the LHC is doing a great job. And so the precision now we already start an era of the precise measurement at the LHC, and now I mean the program is going to measure with quite high precision all the Higgs coupling to Z, W, W, and BB and total. And so here you can have some. This is the kappa F and kappa V. So this is the reduced coupling of the Higgs to fermion. And this is the reduced coupling of the Higgs to gauge boson. And so you see it is quite spectacular. It's consistent with the standard model. The standard model is here. So on the best fit value is within the black circle, and agree pretty well with the at 95 confidence level. It agree with the prediction. Next slide. So after the Higgs-like discovery, so now the LHC is running with quite high energy, 13.6 and later maybe 14. So the improvement of the Higgs-like mass, we can improve the Higgs mass-like and also the Higgs-like coupling measurement, and maybe find a clear hint of new physics. Well, till now there are some indication, but and also accurate measurement of the Higgs-like coupling to standard model particle would help to determine if the Higgs belongs to standard model or to some other extension of the standard model. So they said in the beginning, so most of the many extension of the standard model, they have some high representation, and this high representation of the Higgs predict singly charged Higgs, not only neutral Higgs, but also charged Higgs, and in some case, even doubly charged Higgs, like in the type 2 seesaw model. You can have doubly charged Higgs. Okay, this said, so I will just introduce the 2X doublet model, which is a very simple model, and because it is the model that we found in the minimal supersymmetric standard model. Okay, so in minimal supersymmetric standard model, because if you want to give a mass to fermion and quark, you need in the standard model. So because if you want to give a mass to up and down quark, you need to introduce the complex conjugate of the Higgs field. And we know in supersymmetric theory, so the complex conjugate operation is forbidden. So you need at least to have 2 Higgs doublet model. One will give mass to up quark, and the other one will give mass to down quark. This is the minimal supersymmetric standard model, and this is one of the motivation of the Twiggs doublet model. Also, you can also have within the Twiggs doublet model, you can have some CP violation in the scalar sector, and this will give you extra sources of CP violation. And we know from some measurements that sometimes there is not enough CP violating phase in the CKM matrix to explain all the phenomena of CP violation. And so that's why, for example, an additional source of CP violation is welcome. And so the Twiggs doublet model, for example, can exhibit some CP violation in the scalar sector. So this is the scalar sector for the Twiggs doublet model, and we have two doublets. You have several parameters here, and so you have this lambda 6, which I put in red here because those terms, so they introduce some, they violate what we call the Z2 symmetry by dimension 4 term, and this could be quite dangerous for the flavor changing natural current. Okay, so that's why in some version of the standard model, we assume that this lambda 6 and, of the Twiggs doublet model, we assume that lambda 6 and lambda 7 should vanish in order to restore this Z2 symmetry. And we allow only some soft violation of this Z2 symmetry by dimension 2 terms. In this model, if you want to have some explicit CP violation, you just, if you take, for example, the imaginary part of M12 times lambda 5, which is non-zero, you can get some explicit CP violation in the Higgs sector. Okay, next slide. And so this is the Yukawa Lagrangian. So in the general model, you can couple both Higgs can couple to all fermions, but this version will lead to some flavor violation, flavor changing natural current at 3 level. So if you do it that way, so in order to avoid this kind of thing, so we ask that every doublet couple to some type of fermions. For example, in type 1, for example, phi 1 couple to fermions, but phi 2 does not couple. So in type 2, for example, phi 1 couple only to bound quark, and phi 2 couple to phi 1 couple to down and left charge lepton, and phi 2 coupled only to up quark, and so on. So in type 3, so this configuration, you can just set some of the Yukawas here to 0, and you can get some the picture. Anyway, I will explain. So maybe for type 1 and type when only one doublet couple to fermion, but the other one does not couple. In type 3, what we call the lepton specific model. So it's with this kind of setup, means that phi 1 coupled to lepton, and phi 2 couples to up and down quark. Okay, next slide. And so this is just the Feynman rules you can get from the above Lagrangians. And this is the Higgs coupling to gauge bosons that you can get from the covariant derivative. Okay, next. Okay, so we have some rules. So because since in this model we have 2 neutral X and two CP even and 1 CP odd. So even if you have much more CP even, so we know that the Higgs coupling to 2 gauge boson. So if you identify one of the Higgs to standard model X, so this coupling should mimic the standard model coupling of should mimic the coupling of the standard model X to 2 gauge boson, which is we now measure quite well. So, and you have this sum rule. So if you have several Higgs, so then this should share this coupling to gauge boson. Okay. So if one mimic the standard model coupling, which is almost full strength, so the other one should be close to should be quite small or close to zero, which this is what we call the decoupling limit. Okay. In the decoupling limit, so one of the Higgs will mimic the standard model one, and the other one will couple with a very small strength to the W gauge boson. And you have other some rules of these gauge bosons between them. For example, the coupling of two Higgs boson to two Ws, and the coupling of charge Higgs to W, and CP even should be 1, and so on. Okay, next slide. Okay, so those are the coupling of the different Higgs. This is the light CP even, and the heavy CP even, and the CP odd. And in the second line is the coupling of charge Higgs to fermions. And so these coupling depend on what we call this tangent beta, which is the ratio of the VEV to VEV, and also the mixing alpha, which is the mixing between the CP even and CP odd terms. Okay. There are some coupling which I wrote in red because there's one key parameter in this model, which is tangent beta. So, for example, this coupling of A to bound quark in type 2 is proportional to tangent beta, like in the MSSM. And so this, if your tangent beta is quite large, so this coupling becomes extremely large. This one also, if behaves like 1 over cosine beta, but if tangent beta is quite large, this behaves also like tangent beta, and also the others. And this maybe we need it later for some discussion. Okay, next slide, please. Okay, so we will use this 2x doublet model, and so we link, of course, the model to what we call Higgs bound and Higgs signal, which take into account all the experimental constraints from LEP, Tevatron, and LHC. And also we use some theoretical constraints. So the theoretical constraints we are using is the stability of the 2x doublet model potential, okay, which requires that it should be bounded from below, which means that there is no direction in field space along which the potential becomes negative, because if you go at quite large value of the field, so the potential should remain positive. Okay, and so this gives you several constraints which we can reproduce. So lambda 1 must be positive and lambda 2 positive, and also you have this relationship between the other parameters. So if you ask that the vacuum of the model is a global one, so you get this kind of constraints here. And also there is, if you do the perturbative unitarity, means if you do the scattering of the W to W, and also the scattering of the Higgs between the Higgs themselves, there is a set of more than, I think, 24 channel. If you write all the channel for the gauge scattering and of the Higgs scattering, some of them, they will give you some constraint, and you take the amplitude at high energy, and you require that the amplitude at high energy should remain perturbative, means should satisfy the unitarity bound. And so you get some constraint on the amplitude. You get the constraints on the amplitude of this coupling that contribute to the scattering. Next slide. Okay, so 2x doublet model spectrum and constraints, as I said, so we use this 2HDM calculator. Okay, this is a public code. For B physics, we use this code by Nazila, which is super ISO. For 2x doublet model type 2 and 4, so there is a severe constraint on the charge Higgs from B to S gamma. If you want to satisfy the measurement from B to S gamma, so the charge Higgs should be heavier than 800 GeV for any value of tangent beta. And so this if you believe in this constraint. So this means that you cannot, if you see some charged Higgs at the LHC, so because the charge Higgs at the LHC, as I will explain later, so you can only do some physics if the charge Higgs is less than 500 GeV or 550 up to 60. So which means this constraint here puts the 2x doublet model type 2 out of range at the LHC. In the 2x doublet type 1, so there is no limit on the charge Higgs for at least for tangent beta greater than 2. So you can search for charge Higgs as light as 80 GeV or 100 GeV, as I will explain later. Okay, next slide. Okay, so now we'll discuss the production of the charged Higgs, the mechanism of production of such charged Higgs particle. So there is a very nice review written in 2016 by a group of people, including myself. So if the charged Higgs is light, means is less than m top, so you can produce the charged Higgs from top decay. So because since the TT bar is copiously produced at the LHC, so the cross section of TT bar cross section is huge. So if you look to if your charged Higgs is coupled to top, so then you can and if the charged Higgs is light, so you can look for the top coming from top decay. You can look for charged Higgs coming from top decay. Okay, this gives quite large cross section, and this is actually what is for light charged Higgs. We both CMS and Atlas, they search for charged Higgs coming from this process. Okay, there is also various direct production mode. For example, glue B goes to TB, T charged Higgs. Glue going to TB charged Higgs. So those are almost twin process. This is 4 flavor scheme and this is 5 flavor scheme. And you can also produce the charged Higgs that through glue going to WH in association with the W, but this is loop mediated, which means that it's quite small because it goes through triangle and also through box diagram. Okay, you can also produce a pair of charged Higgs, but it comes from glue fusion, and so this also is loop suppressed because it is produced only by triangle and from box. You can have BB bar, but there is, as you know, there is less chance to find B in the protons. So this cross-section, when you take into account the luminosity of the B within the proton, so this cross-section is quite small also. Okay, so but if the charged Higgs is quite light, so you can produce in pair using this QQ bar, UU bar or DD bar with the exchange of gamma and Z, and so you can get the pair of charged Higgs, or you can produce the charged Higgs in association with one of the neutral Higgs, so which is this process with the exchange of the W. Okay, you can have in the initial state UD goes to W, and then W split to neutral Higgs and charged Higgs bosons. You can also have a resonant production, CS bar going to charged Higgs or CB bar, okay? But this one is suppressed by CKM. This one is diagonal, but still the section could be quite large if the charged Higgs is light. And there is also W Higgs fusion, which is this process, QB going to Q prime charged Higgs. This work I did with Jay Sikli and Kingman Chang from Taiwan. When we started this work, we thought that we got big fish because, you know, for the neutral Higgs, you have the WW fusion. And this cross-section is quite large. After the glue fusion going to standard model Higgs, after this comes the WW fusion going to neutral Higgs. But for the charged Higgs, you cannot annihilate W and Z because in this model, this coupling does not exist. W and Z and charged Higgs does not exist in the 2Higgs doublet model. It exists only in the model with the triplet Higgs. For example, in type 2 seesaw, you can have the annihilation of W and Z. But this is proportional to a triplet valve, and the triplet valve is severely constrained to be small in this kind of model, and so that's why this cross-section is small. You can have this WZ fusion at a model like, for example, in Georgi Mashasek, when you have two triplet Higgs, okay? And there you can have this kind of WZ fusion, and you can produce the charge X in this WZ fusion with quite high cross-section. Next slide. Okay, so this is the W neutral Higgs fusion. Okay, as I say, there is no, you cannot have WW fusion for the charge X. This particle is charged. So you cannot have WW fusion, you cannot have ZZ fusion as well, okay? But you can have this kind of things. So as I said, in the beginning, we thought we got a big fish, but it turns out that there is a strong conciliation. You have the contribution of those four diagrams here, you can see. So this is the top contribution, which is the fourth diagram, this one. The green is the D plus the pseudoscalar, which is somewhere here, okay? Or this one, A or C, so, okay? And the top contribution is B, okay? But when you sum everything, so you see there is a strong conciliation between the top contribution and also the other diagrams, the diagram with the exchange of the neutral Higgs here. And so this at the patronic level, and this is the full hadronic cross-section. So you can see it's the same picture. The red is the top only. The top cross-section means that the charge X is coming from top decay. But when you sum everything, so you have the cross-section drops almost by one, even more than one order of magnitude. And so, unfortunately, this process does not give also quite large cross-section. Next slide. Okay, so the decay of the charge X, the decay is, there are several channels. The charge X can go to tau nu, CS, CB. Charge X, if it's quite heavy, it can go to TB. And you have also the bosonic decay. The charge X can go to W and neutral Higgs, or the charge X can go to W, gamma, and WZ. So the first one, charge X is going to W neutral Higgs. This is what we call the bosonic decay. This I have done with my former student, Rashid Benbri. And we demonstrate that this decay channel could be quite important and could give some quite interesting signature at the LHC. There's two charges going to W, gamma, and WZ. Those are loop mediated, and so they are quite small. In the MSSM or in the Twiggs doublet model, they are quite suppressed. Unless if you allow for some large scalar coupling, which is constrained by the unitarity constraint, and that makes this decay channel quite small. This branch ratio could be of the order of 10 to the minus 3 to the 4 in the best case. Okay, next slide. Okay, so here I show you some the branch ratio of the charge Higgs. For example, going here, the branch ratio going to tau nu. This the blue, no. Yeah, this is the charge Higgs going to tau nu. Is this one? The one that is decreasing. So, and the charge Higgs is going to WA. This is the bosonic decay. So as you can see, so when the bosonic decay charge X can goes to WA, so the branch ratio becomes the dominant one. Okay, so you can see it in both cases. This is for type 1, and this is for type X. And I took here MA equal 65. There is no, it is still okay with the with lab data and also with the LHC and so on, and Tevatron data. Okay, and so this is what we call the bosonic decay of the charge X. So it could be quite important. especially in type 1. So it's all time quite dominant. In type X, so there is some mismatch, so it becomes dominant when this one is when the charged Higgs is quite heavy. It means that this WA is almost on shell. Next slide. Okay, so this is a search by Atlas and CMS. This is by Atlas, so you can see the limits on the production of the charged Higgs from this channel TB charged Higgs, and charged Higgs go to tau nu. Okay, and this is for a heavy Higgs. Okay, heavy charged Higgs, and this one for light charged Higgs. This can from 90 to 160, and so this is the limit on T going to B charged Higgs times the branch ratio of charged Higgs is going to tau nu. So the limit of the branch ratio of T going to B charged Higgs is given by this quantity, because the charged Higgs, the top decay can go to B charged Higgs and BW. So BW is the dominant one. So, but this one is still, this branch ratio is quite small, but since, as you know, so the cross-section, TT bar cross-section is huge. So that's why this channel can still set a limit on the charged Higgs mass and tangent beta. Okay, so this depends on charged Higgs, of course, and tangent beta. Okay, next slide. So this is the interpretation of the same search in the MSSM. This is the MSSM, this scenario which we call MH mode. And so you can see in the MSSM, charged Higgs is excluded up to 160. Okay, 60, there is no charged Higgs to search, so there is only, you can look for a charged Higgs quite heavier than, and it requires also tangent beta should be quite moderate, not too heavy. But there is, next slide, please. Okay, in the MSSM, I said that the charged Higgs is excluded from if the charged Higgs is less than 160. But this, if you assume that the light CP even is the standard model like Higgs, and the heavy one is heavier than 125. But there is another scenario when you assume that the standard model Higgs is the heavy one, and little h is less than 125. And this is in the MSSM, and you see even in the MSSM, you can still have a charged Higgs between 150 and 170, which is not excluded. Okay, and in this white area, so you have because the charged Higgs decay to this bosonic decay. It decays to W, little h, or WA. Okay, and so for example here in this small area, so you have A is 130, okay, and if the charged Higgs is the order 160, so it can decay to W off shell and CP odd, and you can have dominance here in this area here, because for light charged Higgs, the lap limit is very strong, but the lap limit apply only if the charged Higgs decay to tau nu, or to the light fermions, to CS or whatever. But if the charged Higgs decay to W and lit H, for the moment there is no search in this channel. There is some search at lip, but there is some limit which we take into account, but it's not very constraining. And now both CMS and the Atlas, they start searching for this bosonic decay as well. Next slide. Okay, so for example, if I take the CP odd at 40 GeV and I do the limit from LHC, if I say that WA is not open, means I take A quite heavy. So if I take A quite heavy, So I can exclude the charge X up to 160 for some small tangent beta. So if tangent beta becomes large, so I can exclude charge X up to 140, for example. This is what you see in red. But once I open the bosonic decay, I open WA, I can reduce the red area to the green one. And I can have a charge X as light as 130, 140, for example, if I can manage to open one of the bosonic decay. Okay, next slide. So this is the search done by, actually the yellow curve, what you see, the search has been done by LEP before the shutdown in 2001. And so the exclusion limit of the order of 85, but it could be smaller, so in some case. And they consider, for example, here CPO of the order 12J or 30J GeV. And so they have this exclusion here. So now CMS, as I said, CMS also is searching for this kind of decay channel, what I call the the bosonic decay. And so they look A going to W, charge X is going to AW, and A goes to 2 muons. Because this is motivated by, in the next minimal supersymmetric standard model, you can have CP-odd, which is quite small because it behaves like an axion particle. And so it can decay to it could be extremely light. And so if it is extremely light, so it won't decay to tau tau and VV bar, it will decay dominantly to either a mu plus, mu minus, or 2 photons with the branch ratio, which is quite large. So that's why CMS, they are searching for this kind of channel, and there is already some limit on this kind of models. Next slide. Okay, so this is the picture now of the 2x double model. So if you do fit of the 2x double model parameters to with the LHC data, so you can realize that the LHC data is pushing you to the decoupling limit, because this cosine beta minus alpha is the coupling of the standard model Higgs to 2Ws or to 2Z. And so, no, sorry, this is the coupling, this is the opposite one. This is the coupling of the heavy one to 2Ws. Cosine beta minus alpha is the coupling of the heavy X to 2Ws. Okay? And so the data tells you that cosine beta minus alpha should be very small, of the order of between 0.1 minus 0.1 and 0.1. Okay? This is for type 1. In type 2, for example, same picture. So this cosine beta minus alpha should be in the white region here. This, if you assume that the light one is the light CP even is 125, and the other one is quite heavy. So this cosine beta should be very small, which means that sine beta minus alpha should be close to 1. And sine beta minus alpha is the coupling of the standard model Higgs to 2Ws or 2Zs. So this should be full strength. And this means that we are almost in the decoupling limit. Means that the heavy coupling, the heavy Higgs coupling to 2W becomes very, very small. In this work, I will assume the inverted scenario. Means I will assume that the light one, the heavy one is the 125 GeV, and the light one is less than 125. And this scenario, to be consistent with the LHC, we require that cosine beta minus alpha, which is 1. So in this case, it is cosine beta minus alpha, which is close to 1, and sine beta minus alpha, very close to 0. Next slide. Okay, so as I said, in the alignment limit, so cosine beta minus alpha is close to 1, because the heavy CP even mimic the standard model, the heavy CP even mimic the standard model Higgs, okay? Means that the decoupling of also of this heavy Higgs to pair of fermion is close to 1, because we are almost in the decoupling limit, okay? This coupling is close to 1, and this one becomes 0. The other one, the light one, coupled to 2 gauge boson, should vanish or close to 0. Okay, but in this scenario, if this light CP even is extremely light, you can have the standard model X can decay to 2 CP even, or to 2 CP odd if the CP odd are quite light, or to Z and the CP odd. All this is taken into account, so you should the sum of those 3 branch ratio, for example, should remain less than 10%, which is the error, the allowed error of the LHC data. So means that the small rooms that the data will allow is that the sum of those, I can call them non-detectable channel, should be less than 10%, because we know that this Higgs goes to B bar with almost 60%. It goes to W with some 15% and ZZ. So we know everything's quite well. And so the only room that remains for this non-detectable channel is within the experimental error, which is of the order of 10%. Okay. So if those 2 particles, in some case, they could be extremely light, those 2, and this you have to worry about the decay. Z can decay to H and A. And since this coupling is proportional to cosine beta, this is close to 1 and could be very important. And the Z decay, we know since a long time ago, since 2000, before the shutdown of LEB, we know the decay width of the Z particle with the very, very high precision. And so this decay, if it is open, it should satisfy this, it should be also stay within the experimental uncertainty that we know on the Z width. Okay, this also is included in our code. So, and we also require the electroweak precision test measurement, which means that we impose the S, T, and U constraint, because when the splitting between, we know that this electroweak precision test observable depend on the new physics and depend especially on the splitting between the particle that contributes to the W and Z polarization loops. And so if this splitting is large, so it could contribute with with significant contribution, and it could violate the electroweak precision test observable. Okay, and also, so here we assume that this the heavy one is 125 and is consistent with the LEB CDF and also with the new measurement of the W mass, not from Tevatron, but from CMS and Atlas. Okay, next slide. Okay, so this is the picture. If you scan the parameter space of this model and you require that S and T parameters should be satisfied, so you get some there is still some point which are allowed by the electroweak precision test observable, for which the light CP even and plus the CP odd are less than the Z. If you take those 2 quite heavy, so there's still in the right plots there's more points, so you can see, and this is give you the splitting between the charge X and the CP even, and also charge X and the CP odd. Anyway, so there is still a lot of points in the parameter space that are consistent with the electroweak precision test observable. This is what I want to say. Next slide. Okay, so in the, as I said, in the 2x doublet model type 1, so this coupling could be very small, cosine alpha, because alpha is the mixing between the CP even component. And so it's a free parameters. I can simply take alpha close to pi over 2, and I can kill all the coupling to fermion. This is what we say, this Higgs becomes fermiophobic. If I take alpha very close to pi over 2, this coupling becomes 0. This is what we call Higgs is fermiophobic when cosine alpha goes to 0. Okay, so in this scenario, so Higgs does not couple to 2Ws because it's proportional sum beta minus alpha, which is close to 0 because of the decoupling limit of the model. So it means that this light Higgs won't decay to WW and ZZ. Okay, so then the Higgs going to gamma gamma could reach 100%. Okay, it comes from the charge Higgs can go to gamma gamma with 100% branch ratio. And the charge Higgs W and little h, this coupling is proportional to cosine beta minus alpha. Okay, and so it's close to 1. The light Higgs can be produced from, as I said before, so it can be produced from T decays, but it can be also produced from those two channels. I'm going to discuss those two channels here. The charge, the charge Higgs produced from PP bar through the W, and also by exchanging gamma and Z to pair the pair production of the charge Higgs. And I will try to convince you that those two channels could be much more important in some case than the production coming from the top decay. Okay, so in the top decay, for example, you have TT bar, and one T goes to BW, the other T goes to B charge X. Okay, and so if the charge Higgs decays to the bosonic decay, W little h, so you would have two Bs, two Ws, and neutral X. If this Higgs goes to gamma gamma, you get 2 photons from TT bar. But from the associate production of the charged Higgs with the neutral Higgs, charge Higgs little h will go to W little h. If the little h goes to 2 Higgs, you get 4 photon signature plus W. And we know that 4 photon signature, so it has quite small background. And there is many ways to suppress the background coming from 4 Ws. Okay, I hope it's clear. So this is the point I want to discuss. So this is the bosonic decay of the charge Higgs in this model. For example, the charge Higgs is going to little hw, or charge Higgs is going to aw. So as you can see, this branch ratio could be quite large, almost 100% as function of the charged Higgs mass. And here is the splitting between the charged Higgs and the neutral Higgs. Okay, so this bosonic decay could be extremely large. This is the main point here. Next slide. Okay, and so same thing. So if you look to Higgs to gamma gamma, it could be also, as I said, so in this model, the Higgs does not decay to 2 fermion because it is fermiophobic. It does not decay to 2W because the coupling to 2W is suppressed by sine by beta minus alpha, which is close to 0. So we are in the coupling limit, this one, because the heavy one, which is the standard model X. So this one has very small coupling to W. So the only coupling that remains is Higgs going to gamma gamma. You know why? Because inside this, because Higgs to gamma gamma, you have W loop, you have the top loop, and you have the charge Higgs loop. Okay, the W loop is very small in this case because the Higgs coupled to Ws is very suppressed. The Higgs coupled to top, the top contribution is also small because the Higgs is fermiophobic. So there is only the loop by the charge Higgs, and that's why the Higgs to gamma gamma is full. It could be 100%. Okay. And here I show you once again the branch ratio of the charge Higgs on the right plot. You see By the way, so when you see that the Higgs gamma gamma is dominant, so you can check that cosine alpha is very small. So means that the color of the point here becomes close to the black color. So when cosine alpha is quite large, so you see you have yellow color, which means that the branch ratio of Higgs going to gamma gamma is very small. But there is some point when the branch ratio could be very large. Okay, the bosonic decay also could be dominant, 100%. Next slide. Okay, so this I did the comparison from the charge X coming from top production after T decays to charge X, and here the associate production of charge X with neutral X. So the diagonal is when these two cross-sections are the same. So you can see there are a few points when the cross-section of the associate production of charge X with the little h could be bigger than the production coming from TT bar. Okay, well, there are a few points, but if we do quite very detailed scan, we can find other points in this area. Okay, so for this scenario, so there are some parameter space points when the associate production of charge X with the little h is larger than the cross-section coming from the top production. Next slide. Okay, so here we compute the cross-section of the charge X in association with little h as function of the little h mass. And of course, so it is suppressed by the kinematic. When the little h becomes heavy, so the cross-section is decreasing. But you can see, so for light charge X and for light CP even Higgs, so the cross-section could be quite bigger than 1 picobar. This is 10 to the 3 femtobar. Okay, and so here we compute the cross-section of the charge X in association with little h, and charge X goes to WH, and the 2 little h goes to 4 photons. So it is the cross-section for 4 photons, and we let the W decay leptonically. So this is L and 4 photons. And you can see we have, we select a few benchmark points, which you can see here. So 1, 2, 3, 4, 5, and the cross-section is quite large. It's more than, in some case, more than 100 femtobar cross-section. So the points are here, and you can see that the branch ratio of Higgs going to 2 photon is quite large. And the cross-section is, some cases could be few picobar. Okay, next slide. So at what time should I stop? So
you are free, Doctor. Please finish in the time you want.
Okay. Okay, so we did some cut and selection efficiencies. So we require the pseudo rapidity to be when, well, this, you know, if you do this kind of Monte Carlo analysis, all photons should have, we took actually the same condition that Atlas and CMS use. So PT of the photon should be greater than 10 GeV. The charged lepton PT should be greater than 20 GeV. And we took also the opposite case. So if the PT of the photon is greater than 20 and the opposite one, the PT of the lepton should be greater than 10. The reducible standard model W plus 4 gamma, as I said before, is very small. So it's less than 10 to the minus 6 picobar. So we define the efficiency by this ratio, the cross-section with the cut, without cut, and over the cross-section without cut. Okay. And so you see here, we took this benchmark scenario and we compute the efficiency. And so you can see there's some scenario when the efficiency, this is the epsilon, some values here where the efficiency is quite large, 0.31, 0.3, something. Okay. And so Next slide. So we take the cross-section to 4 photon times the efficiency, and we calculate this stuff, as you can see here, for the selected benchmark point. So we still have quite large cross-section, so of the order of more than a few femtobars. Okay. And same thing in this case here. This is for the PT of the photon greater than 10, and this is for the PT of the photon greater than 20. And so it's almost the same conclusion. Okay, next slide. Okay, if you go a little bit before, so the full Monte Carlo analysis at the detector level show that the W4 gamma signal is very promising. We did actually 4 Monte Carlo simulation, and we could extract the signal. I mean, Higgs going to 2 photons quite nicely. Okay. Next slide. Okay. So this is just for the predicted significance as function of sine beta minus alpha. Okay, next slide. Okay. So, that one. Is this Higgs to gamma gamma ruled out or not? Because many times people say that, well, this Higgs to gamma gamma has been searched at lab and so on. So that's true. It has been searched at lab. It has been searched at Tevatron. There is a strong limit on this Higgs going to gamma gamma. But we check very carefully this scenario, and we find that using the Tevatron and the lab limit, and we still find that our scenario is consistent with all the data available. Okay, so but Atlas also has Atlas did a search in 2015, and recently they update this search here, this one. I don't have the reference here, but I saw an update of this this search here. So they look for standard model Higgs production, and the standard model Higgs decay to 2 CP-odd, and the 2 CP-odd goes to 4 photons. This again is a search that is next minimal supersymmetric standard model motivated, because as I said before, in the next minimal supersymmetric standard model, the CP-odd could be axion-like. Well, if you take this this Pechi-Quinn symmetry breaking terms, if you take it, if you tune it so you can make this one to behave like axion, and it will decay only 2 photons. So with A goes to 2 photon is the dominant decay one. So that's why the search for this kind of thing. But we took this search here, okay, and we applied for our case. We require that the heavy Higgs decay to 2 CP even, and the 2 CP even goes to 4 photons. I will try to convince you that we did how we did this work. So if you go to next slide. Okay, so we take those 2 channels. Higgs go into 2 CP even, and the 2 CP even goes to 4 photon, and Higgs go into 2 CP-odd. 2 CP-odd goes to 4 photons. The amplitude for the Higgs coupled to 4 photons, the 2X, this system for 2X coupled to 4 photon, because those are CP even, so it behaves like this. So you have this Lorentz structure, because this one are CP even. But for the pseudoscalar, because those are pseudoscalar, so you have this Lorentz structure. Okay, so we take the square amplitude of this amplitude and also for the other one, and we find that they behave exactly the same. K1 times K2. K1 is the momentum of the initial state Higgs, and K3, K4 are the momentum of the K1, K2, K3, K4 are the momentum of the 4 photon in the final state. Okay, and you see whether the amplitude coming from CP even or CP odd, so the amplitude is exactly the same. with some normalization factor, which is different. So we do this normalization, C, and here you have D, okay? And we did some distribution. If you go to the next slide. We did some distribution to compare between, this is for the CP even in the left and on the right of the CP odd. So you can see the distribution are quite similar, okay? And we conclude that we can use actually this, because the data is available only for the CP odd, okay? And so we use this data for the CP even and try to set constraints on this scenario. Next slide. Okay, so here is the same. So the distribution, so on the left is for the CP even and the right is the CP odd. And so you can see the distribution are still the same for different pairing of the photon in the final state. Okay, next slide. Okay, so if in order to project the sensitivity of the future LSC run for 14 TV, we have done rescale because the data at 2015, it was only for 8 TV. So we did the rescaling and we could do the projection from 8 to 14 TV. Okay, so we apply the same constraint that has been, the same cuts that has been used by Atlas, which are listed here. Okay. And we try to see if the tweak doublet model is ruled out by this Atlas search or not. So the answer is in the next slide. So, okay. So this is the Atlas data is the first band, the green band is for the 8 TV. And the other one is the projected. The next band here, there are two band, green band. The first one is the 8 TV data, and the second one is our projection for 14 TV. So at 8 TV, we could, when we do the scan, so we could exclude some point, but you can see that there are several points which escape from this constraint. Okay. And same thing, if you do also the projection for the 14 TV data, there are still many points which escape the Atlas data from both 8 TV and 14 TV data. Okay. So which means that this scenario, so we impose the LEP constraint, we impose the Tivatron constraint from fermiophobic search, and we also impose this limit from Atlas Higgs going to 2 CP odd, and the 2 CP odd goes to 4 photons. Next slide, please. Okay, so here we compare the, this is the cross-section of the charge Higgs coming from TT bar, 2T, and 1T goes to WB, and the other one goes to W, and Higgs goes to 2 fermions. Okay, so you can see it here, you can read it here. So TT bar, T goes to BH, and the other T goes to BW, and W and charge Higgs go to WH, and the little h goes to 2 fermions. Okay, so when I call sigma T, this cross section is where the 1 T goes to, is coming from this cross section, sorry. This is coming from TT bar, this is coming from the associated production of the charge Higgs with TB, with T going to BW, and charge Higgs go to W little h, and little h goes to FF bar, 2 fermions. Okay, and this is the cross section of the di-Higgs, what I call the pair of charge Higgs production. You have the bosonic decay of the charge Higgs, and the charge Higgs goes, one goes to WH and the other one goes to WA, and one Higgs go to pair of fermions. Okay, or the opposite. So one Higgs goes to FF bar and the other one goes to a different pair of fermion. This is BB bar, for example, The other one goes to tau tau, for example. It could be 2B, 4 B's, it could be 2B to tau. Okay, and I want to compare this 4 cross-section, the cross-section coming from top production, the cross-section coming from the associate production of the top with the charge X, and the cross-section coming from pair production of charge X, and also the associate production of charge X with the neutral X. Okay, next slide. So we demonstrate that, so this in the x-axis, so this is 2 W's and 4 B's coming from 2T, means coming from TT bar production, and here is coming from the associate production of the X. Okay, and see, you can see there are plenty of points on the associate production of the charge X in the associate production of charge X with the neutral X is the dominant one. Okay. And so we want to warn our experimental colleagues that this could be quite much larger than the cross-section coming from TT bar production. Okay, so same thing here. So this is the cross-section coming from the associate production of top with the charge X. And so same story. So the cross-section coming from the associate production of charge X with neutral X could be quite large than the one coming from associate production of top with the charge X. Next slide. Okay, so here is the same picture, but this is, in this case, we look for the charge X production, the associate production of charge X with the CPOD. And so same conclusion, we have plenty of points when this associate production of charge X with the CPOD could be larger than the one coming from TT bar, or the one coming from the associate production of top and the charge X. Next slide. Okay, so this is the same conclusion. This is 2B to tau, and still the same conclusion. For the black point, I think is for type 3, the lepton specific, because as you know, in the lepton specific model, so the little Higgs will decay dominantly to taus. So that's why see there's some black point here when the associate production of the little h with the charge X could be much larger than the one coming from TT bar production. Next slide. Okay, this is for the previous one was for B. This is for 2B to tau. So same as I said before. Okay. Next slide. Okay, so this brings me to the conclusion. So in the type 1 or type X, there is the region of parameter space which are consistent with the LEP, Tevatron, and some of the LHC data. And this still does not forbid the quite light charge X, means that the charge X less than MT top mass is still valid. I mean, we should look for it. So this is the main point. And I hope I convince you that this cross-section, the associate production of the charge X with the neutral X with the light one, or the associated production of charge X with the CPOD, or the pair production of the charge X followed by charge X decay to W and little h, it could give a cross-section which is quite bigger than the cross-section coming from TT bar. Because from most of the experimental search, so they mainly when they are interested for the light charge X, they look for the light charge X coming from top decay. Okay, and we try to convince them that this scenario should be also looked for. And I think I show you also this scenario when the this associated production of the charge X with the neutral X could lead to some important signature, which is 4 photons and W. With the W could go leptonically. So this is very clean signature. And also we study also this signature when the light Higgs goes to 4 fermions, to B, 4B to B to tau. And we also did some Monte Carlo analysis for all those scenarios. Okay, that's all. Thank you. If there is a question.
Thanks a lot, Dr. Abdesslam, for this interesting talk. And now time for questions. If anyone has question, أستاذ حسين يعني أستاذ حسين لديه سؤال أعتقد ممكن نبدأ به الأول. أستاذ حسين الخالدي. سارة ممكن تعملي unmute للبارتيسيبانت. طيب تمام، يعني يظهر ان سارة مش موجودة. هحاول انا اعمل unmute. حضرتك كو هوست دكتور عبد السلام، ممكن تعمل unmute للبارتيسيبانت.
لا أفقه كثيرا.
تمام. بارتيسيبانت.
Participant, okay. But if I unmute the participants, also the person that want to ask the questions, so just keep it. So I think there is in the chat, there is some question now. Or...
Okay, so maybe I ask you, Abdesslam, until Hussein or other people ask. You said 2 Higgs doublets, charged Higgs has a constraint like 800 GeV.